morning. For this last section of Chapter 10, and this will be for information that will cover or would be covered on 3/27, so for Friday, March 27th class. And today I want to talk about the concepts of polarity and how we look at a molecule like we've been doing from its and get its molecular shape, and how we look at that molecule and determine whether it's a polar molecule or a non-polar molecule. So first, a little background, and what does it mean to be polar? Well, I think we've all probably had the experience of seeing that if you mix water, right, with oil, that they don't mix, right? You can shake them up, and maybe you can get it to sort of mix, but in reality, if you let it sit there, they will separate into two layers. These things do not mix. Well, the question is, why don't they mix, right? And the ultimate answer to that is the polarity of the molecules. They have different polarities, and molecules with different polarities don't tend to want to mix. So let's look at water for first. So water is this molecule here, right? So we've drawn the Lewis structure. And what we see is if we look at the bonds in water, right, that they are made up of a pair of electrons. And each atom donates one of those electrons. But we've talked about this sharing as if they're shared equally. Now, that is sometimes the case. Sometimes the electrons are equally shared among the two atoms. But it turns out that in reality, a lot of the times, we have what we might call unequal sharing. So if we think about on the playground, right, playing tug of war, right, if you have one team that is stronger and can pull harder, right, then the rope or that flag in the middle is going to move closer to their side and not from the other. And that's kind of how it works with the electrons in the bond. That if one of the atoms can pull stronger, then the electrons will move closer to it than to the other. And so that's what happens in a bond like that between O and H, is that the oxygen atom pulls harder and gets more than its equal share of electrons. Now, the ability to do this is called an atom's electronegativity. So each atom is assigned an electronegativity value based on its ability to attract electrons. So when we defined electronegativity, we want to call it as an element's ability to attract electrons within a bond. So oxygen is more electronegative than hydrogen, so it has a higher ability to attract the electrons, which means, on average, those electrons that are, quote, shared will be closer to the oxygen than they will be to the hydrogen. So they're going to be pulled over to the oxygen side, creating what we might call a polar bond, right? Now, technically, we call this a dipole moment, right? And this is kind of how we can visualize it. So if these dots represent the electrons, or where we might likely find an electron, remember, we can't actually know where it is, but if we look at the likelihood of where it might be, we can see that it is more likely to be found over here than over here. So, in other words, the oxygen is getting a larger share of the electron on average, and so that creates what we call a dipole, two poles, right? We create a negative pole on the higher electronegative atom, right? Because the electrons are more likely to be over here, giving a little bit of a negative charge, and we create a positive pole in the lower electronegative atom, where the electrons are less likely to be. So we have a dipole, two sides, positive and negative, where in this case The oxygen, the higher electronegative atom, is the negative pole, And the hydrogen, the lower electronegative atom, is the positive pole. And so this results in what we call a dipole moment. Now in this class, we are not going to dwell on this idea of dipole moments and necessarily which side is positive and which side is negative and by how much. We're going to use a little bit simpler idea just to determine whether these bonds are polar or nonpolar. So if you have a bond that has a dipole moment, it's called a polar bond, or a polar covalent bond if you want to, get a little more specific. Now, how big that dipole moment is, meaning how unequal the sharing is and how polar the bond is, depend on how big the electronegativity difference is. So the bigger the difference, the more polar the bond is, the bigger the dipole moment would be. And so if we think about bonds that are of the same length, because of course the length of the bond has some effect here, and so the length of the bond will vary depending on how big the atoms are, but again, we're not going to get into that level of detail. So if we just think about all bonds as being basically the same length, we can look at just the difference in electronegativity to determine how polar the bond is. So here's a table of electronegativities, and so this is again one of our periodic trends. So if we look at the trends and we look at our main group elements, we can see that as we go left to right on the periodic table, the electronegativity goes up, right? So as we go across a period, the electronegativity gets gradually higher. As we go up a column, the electronegativity gets higher. So if we think about our trends, as you go left to right across a period, electronegativity gets bigger. As you go up a column, electronegativity gets bigger. Or if you want to think about it going down a column, the electronegativity gets smaller. So it turns out your largest electronegativities are up here in your upper right-hand corner, and your lower electronegativities are down here in your lower left-hand corner, with fluorine being the highest electronegative element with a value of 4. Now, these are not values that you'll need to memorize. This table will be provided for you on an exam, etc. You have it in the book for reference, in your study guide, etc. We just need to know how to use these values, and we want to know the basic trends. So the way we use these is if we're looking at a specific bond. So let's say we're looking at our OH bond. Now, if we go back to our table, we saw that O has a value of 3.5 and hydrogen has a value of 2.1. So if we look at this, our delta En is going to be 3.5 minus 2.1. So it's going to equal 1.4. Now, when you're doing these, don't worry about the order. We always want this to be a positive number, so it's an absolute value. So just take the biggest minus the smallest. It doesn't really matter which order. Now, if once we have our value for our difference in electronegativity of a bond, we can then apply our criteria. So if we have a difference of 0 to 0.4, that means we have what's called a nonpolar, or this book calls a pure covalent. I will not use that term. I will just simply call it a nonpolar bond if the difference is small. So what that implies is we have basically equal sharing. If that difference is between 0.5 now, so 0.4 I would still call covalent, nonpolar. If it's above 0.4, so really what that means is 0.5 to 2, then we consider that a polar bond, right? So that's where OH would fall into. It's within that category, so the OH bond would be considered a polar bond. Now, if that difference gets too big, right? If that difference gets to be 2 and above, right? Then the difference becomes so great that these atoms no longer have the ability to share, right? That one atom pulls so hard that it essentially rips the electrons away from the other one, and we end up with an ionic bond, right? We end up with not the sharing of electrons, but the transfer of electrons. So, and this is where we see, if we look at the differences between when we have a metal and a non-metal, oftentimes those differences are 2 and above, or right around 2 and above, and so they can no longer be effectively shared. The more electronegative atom essentially rips them away, and we get an ionic structure, an ionic bond. So that's all there is to it. We just need to look at the electronegativities, get the difference, and we can decide whether a bond is polar or not. All right, so now that we understand how to tell whether a bond within a molecule is polar, how do we then apply that concept to determine whether a molecule itself is polar? So one distinction that we need to keep straight here, and sometimes gets confusing, is that we can have polar bonds, right? And that's looking at an individual bond and how big the electronegativity difference is. But just having a polar bond doesn't automatically make a molecule polar. So we need to talk a little more detail about what criteria we need for an actual molecule itself to be a polar molecule. So let's look at carbon dioxide as our first example. So if we look here, we see the Lewis structure of CO2, right? And we drew this earlier. And notice it has 2 electron groups. So we would say this would have a linear geometry. And so if we were to look at the bonds, right, we would look at the electronegativity difference, and we would calculate that the electronegativity difference for this bond would be 3.5 value for oxygen and 2.5 value for carbon, right? So the difference in electronegativity for each of these bonds is going to be 3.5 minus 2.5, or 1, right? So clearly these fall into the value of a polar bond. Now, if we look more globally at the molecule, we see that we have 2 polar bonds here. We have one here and one here. Now, we use these little vector arrows to represent the direction that the electrons are going. So if we see here, we see that oxygen is more electronegative, so these electrons are going to be going this way toward the oxygen, this way toward this oxygen. Now, when we look at this molecule, it has a linear shape, right? And it has these dipoles pointing in opposite directions with exactly the same molecule, with exactly the same difference in electronegativity. So in essence, these 2 dipoles will cancel out. Right? And that leaves the entire molecule with no dipole. So no molecule dipole. So while this molecule has a polar bond, has multiple polar bonds, it is symmetrical in shape, and therefore the dipoles cancel, and we end up with a non-polar molecule. So that's one example. How can we sort of apply this more universally to multiple molecules or to a wide range of molecules? Well, generally speaking, we're going to look at our molecule and we're going to look at the different bonds. And we're going to draw arrows like we did with carbon dioxide. And these are sometimes called vectors. We'll just refer to them as arrows. And they point toward the more electronegative atom. Now, we also then look at all of these dipoles in the molecule and we decide whether they're going to cancel each other out. So let's take one more example. Let's look at a water molecule. So we look at our Lewis structure, or we can draw it in a more space-filling molecule, and we determined earlier that water had a bent shape. And if we do the difference in electronegativity, right, it comes up to be 1.4. Right? We did that earlier, so it has a difference in electronegativity equals 1.4. So this clearly is a polar bond and a bent geometry. Now, a bent geometry is non-symmetric, right? If we look at this, we see that these angles, right, if we remember, are, about 109.5. And so when we draw these dipoles, right, in this example, they point toward the oxygen, but it doesn't really matter. They could both be pointing out and we'd get the same effect. The idea is that because of the angle here, they don't cancel each other out, right? This one is pointing up and to the right. This one is pointing up and to the left. So the up part might cancel each other out, but the left and right, the up part won't cancel, the left and right will, but we end up with an overall dipole. So we can sort of illustrate it like this, where if we were to separate these dipoles into an up part and a right part, and this one into an up part and a left part, what we see is that the left and right parts, right, might cancel, but the up parts won't. They will add together. So water has an overall molecule dipole that points up. And so because water is non-symmetrical, it's polar, right? So it has a polar bond and it has a non-symmetric shape, so it ends up being polar. So if we take these two examples and put them together, we can come up with some general rules. So as follows: for a molecule to be polar, it must, 1, have a polar bond, so we must have a difference in electronegativity above 0.5, or 0.5 or above, and second, it must also have a non-symmetric shape. Now, what does it mean to have a non-symmetric shape? Well, we've talked about sort of analyzing the arrows, and we can see, that if they're pointing equal and opposite, that they'll cancel. But sometimes it's a little bit tricky, right? So, for example, trigonal planar cancels each other out, as well as tetrahedral, right? Both of these are symmetric shapes. Now, it may not seem so obvious that they're going to cancel. So sometimes we can look at this in a more simpler way, if you will. And we can just simply look at the geometries and just assign them a shape. So if we look at our 6 geometries that we've talked about, right, linear is clearly symmetrical. A trigonal planar, right, is also symmetrical. Right? One way to think about this is if you were to take a ball or a ring in the center here, and then have 3 people stand at exactly 120 degrees apart and pull exactly the same, this would not move, right? Because it's experiencing equal force at these 3 equal angles. So this is also a symmetric shape. Now bent, as we saw with water, right, is non-symmetrical. Tetrahedral, on the other hand, right, just like trigonal, planar, and linear, right, again, if you have in the center and you have 4 people standing at 109.5 degrees from each other, all pulling at exactly the same. So if you had the 3 points of the tripod and somebody exactly above it and they were all pulling exactly the same, again, this center piece would not move. So we get a symmetrical shape for tetrahedral. Trigonal pyramid, just like bent, right? You've taken this symmetrical tetrahedron, and now all of a sudden you've gotten rid of this person up here, and so now you only have people pulling downward, and so the ball is going to move down, and so you end up with a non-symmetric shape here. And this version of bent, again, just like the other version of bent, is also going to be non-symmetrical. So really what we've done here is we've taken all 6 possible geometries and we've just assigned them either symmetrical or non-symmetrical. And what we see is that the ones that have no lone pairs, right, the ones that have only bonds, the linear, the trigonal planar, and the tetrahedral, are symmetrical. The ones that have lone pairs, the bent, the trigonal pyramid, and the other version of bent, are non-symmetrical. Now, there is one sort of caveat that we have to put here, is that these designations are perfectly good and will hold as long as the atoms bonded are all the same. What I mean by that is that this would be fine if we apply it to something like CH4, right? Where all 4 of the hydrogens, all 4 of the atoms around the carbon in its tetrahedral are going to be the same. But if we all of a sudden change some of these to different, so if now one of these is chlorine and the other 3 are still hydrogen, then because the difference in electronegativity in all the bonds is not the same, the pulling won't be exactly the same, and again, it won't be balanced, it won't be symmetrical. So all of a sudden, now we have something that is symmetrical geometry, but is not really symmetrical because all 4 are the same. So we need to watch out for examples where we have a symmetric geometry with all 4 bonds, but because all of the atoms aren't the same, it actually ends up being a non-symmetrical shape, or a non-symmetrical molecule, and therefore might be polar, right? So the idea is that CH4, right, is going to be non-polar. This molecule, because it now has a non-symmetric shape, would be polar. So this can have a big influence on whether the molecule is polar or not. But ultimately it comes down to answering these 2 questions. Does it have at least one polar bond? Does it have a non-symmetric shape? If you say yes to both of these, then you have a polar molecule. So that brings us back to the question that we opened up this section with, right? And that is, why do oil and water mix? Well, if we go through, we just determined, right, that water is a polar molecule. Now, it turns out that oil, right, is a non-polar molecule. And what we see is that polar molecules, because they have these dipoles, right, they will strongly interact with other polar molecules, because the positive end of one of the molecular dipoles can interact with the negative end of the dipole in another molecule. And so you get these positive-negative attractions that hold the molecules together, kind of like the south end of one magnet is attracted to the north pole of another magnet, right? And so those poles will stick together. But if we mix polar with nonpolar, they will tend to repel each other, right? They don't like each other because a polar molecule can't make that same attraction, right? There are no positive and negative poles here, so it can't make the same strong attraction that it can with other polar molecules. And so this is kind of like taking a mixture of some magnets that will attract each other and mixing them with some non-magnetic particles, right? These things will not stick to each other, right? They won't mix. In fact, they'll repel each other, right? All the magnetic ones will try to stick to each other and exclude the non-magnetic particles. And it sort of works the same thing with polar and nonpolar, right? All of the polar water molecules will stick to each other, pushing away the nonpolar oil molecules, thus the two materials separate. So we have a general saying here that kind of sums this up, and that is that like dissolves or mixes, if you will, like. So again, like dissolves like, or like mixes with like. And with the like here is the polarity. So polar molecules will dissolve or mix with other polar molecules. Nonpolar molecules will dissolve and mix with other nonpolar molecules, but they don't tend to like to mix with each other. So we can look at this sort of picture the same way. So this is our magnetic and non-magnetic spheres. And we see that, and you've seen this with kids' toys, or if you deal with little magnet spheres, right? All the magnets want to stick together, and any non-magnetic particles would be excluded here, right? And so we can apply the same thing to the water, right? All of these water molecules being polar, they will interact. The negative side of one dipole will interact with the positive side, and another molecule of water, like magnets, and so they will form nice strong interactions at the exclusion of these nonpolar oil molecules. One example of this from everyday life is the idea of how soap works, right? So we've all used soap, right? And soap does a very good job of getting rid of oil and grease and grime, right? Whether it's out of our hair or off our hands, etc., right? And so how is that possible, right? So we've just said that water and oil don't mix, right? So if you've ever tried to, take a shower and wash your hair without shampoo, or if you've ever tried to wash dishes, that have, food stains and these kind of things without any soap, right? You realize it doesn't work very well. And you may have even seen, if you have, oil, like if you've cooked meat or something and you don't use soap, that oil just kind of pools up, makes little oil bubbles or oil drops in the water, right? Because they won't mix. So how does soap make them mix? Well, essentially, the molecules in soap serve two functions. They have two parts. They have a polar part, what we call a polar head, and they have a non-polar part, which we call the tail. So this molecule kind of acts as a bridge, if you will, right? The polar end reacts with water or attracts the water. The non-polar end will attract the grease. And so this can act as sort of a bridge, connecting the oil that's attracted here, to the water that would be attracted here. And so that allows the oil molecules to be combined or combine with the water, because the soap will dissolve in the water and it'll bring the oil along with it, because that oil is attracted to the tail of the soap molecule. So the soap allows the water and the grease to mix, which allows the grease to be removed from your hands and stay dissolved in the water and flow down the drain. So soap, again, acts as that sort of bridge that allows the grease to stick to the soap molecule. That soap molecule can then strongly interact with the water, so the oil gets kind of drug along with the soap molecule to dissolve in the water. All right, so let's finish up our discussion of polarity and polar molecules with a couple more examples. So we'll continue on with the examples that we did in the last section, and that's NO3- and SeO2. So at that point, right, we drew the Lewis structure, and we determined that NO3- had a trigonal planar geometry, right? 3 electron groups, 3 bonds. And so how do we determine whether this is a polar or non-polar molecule? So again, we have to do 2 things, right? We have to determine whether it has polar bonds. So we look at the difference in electronegativity. So if we look at our table, we see that oxygen has a value of 3.5 and nitrogen has a value of 3.0. So our difference in electronegativity equals 3.5 minus 3.0, 0.5. Now, while not very polar, this would meet the first question, right? It has polar bond. So we could say yes to that. Now the second criteria is the shape. So the trigonal planar is a symmetric geometry, right? We have 120 degree bond angles, and so all the dipoles would cancel out. We could, if you wanted to draw this out, we could, right? And we would see that we have arrows running here. And so we have a symmetric shape, right? Trigonal planar, right, is a symmetric shape. So while we can answer yes to this question, right, we have to answer no to this question, right? Remember, our 2 criteria is polar bonds, non-symmetrical geometry. So while this has polar bonds, it has a symmetric shape. So this molecule would end up being non-polar. So let's look at our second example, SeO2. So we've done the Lewis structure. We determined it has a bent geometry, right? And it's with bond angles that are going to be slightly less than 120 degrees because we have 3 electron groups. So if we look at our electronegativity difference, we have a value of, again, 3.5 for oxygen. Selenium is 2.4. So we have a difference in electronegativity here of 3.5 minus 2.4, or 1.1. This again is definitely a polar bond. So we can say yes to that one. So in terms of the symmetric shape, right, well, if we look at bent, right, bent is a non-symmetric shape. Right? No matter how we do this, right, the arrows won't cancel out. So we would have one going like this and one going like this. And so they are not going to cancel out. So we have a non-symmetric shape. So we would be able to give this, again, a check mark, right? Because now we've answered our questions. Yes, it has a polar bond. Yes, it has a non-symmetrical shape. So answering both, yes to both, we can determine that SeO2 would be a polar molecule. All right, so that summarizes, kind of concludes what we want to talk about. And the overall picture is we want to be able to take a single molecule, right? And we want to be able to take it through the whole process, right? We want to be able to look at a molecule, draw its Lewis structure, determine its molecular shape, and based on those ideas, we want to be able to determine whether it is a polar or non-polar molecule. So again, that assignment that is due on April 2nd, that's again, molecular shapes activity, right? Lewis structure molecular shapes activity under Chapter 10 in Talon, that will give you practice in all of these, right? It's going to ask you to look at various molecules and go through this whole process, right? To determine the Lewis structure, determine the geometry, and determine whether the molecule is polar or that. So be working on that. Don't leave it till the end, right? There's quite a few molecules to look at there. So again, that's going to be due on April 2nd. You're going to submit that electronically on Talon. And again, there'll also be more practice in the Chapter 10 homework, which is due on April 3rd. So have a great day. If you have questions on any of this material, please reach out via email, via Remind, or one of my live office hours, which I'll be holding during the week. Look for those times to be posted again on Talon.